Okay, so let's look at entropy more closely. Again, it's a measure of disorder, and everything has an inherent amount of entropy. So, whether it's in vibration of bonds, rotating in space, translation, which is just moving in space, as long as the temperature is greater than 0 Kelvin, which, and then I have parentheses here, that's actually the third law of thermodynamics, which is that at 0 Kelvin, there's no movement. So you could have zero entropy if you were at 0 Kelvin. We will not be doing chemistry at 0 Kelvin, so everything will have some sort of entropy inherent to it. So for the states, we've kind of gotten at this with the examples already. If you look at the entropy of a solid compared to a liquid compared to a gas, the entropy of the solid is the lowest and the entropy of the gas is the highest. So, right, if we're looking, I guess I've got right to left arrow going first. So from the gas to the solid, if we're moving in that direction, things are getting more ordered. So more ordered means less disordered. So more ordered means lower entropy. More disorder, which if you go from left to right, things are getting messier. Messy means more disorder means higher entropy. So we can practice with predicting the sign of delta S. So would it be positive or would it be negative? And right, an increase in disorder means a positive delta S. So positive delta S is an increase, negative delta S is a decrease. So solid to a liquid. Well, I mean, just based on the ranking that we did, a solid to a liquid would have an increase in entropy. So my delta S should be greater than 0. A solid to a gas. Again, everything is increasing in disorder. It's getting messier. So we have a positive delta S. A gas to a liquid, we're going from spread apart, super fast moving molecules to they're still moving fast, but they're in a more confined space. They're all touching each other. This would be a decrease in entropy, so delta S would be negative. Some others, right? We talked about solid sodium chloride dissolving. This is an increase in entropy. And then, because it's going to come up in some reactions, delta N, so for a gas specifically, if the number of moles of gas in the reaction increases, your disorder increases. So this is saying more gas moles means more disorder. If the number of moles of gas is decreasing, then the change in entropy is negative. You're getting more ordered. Now, we'll have reactions that have the number of moles of gas changing, but we'll also have other things changing. So don't forget to look at the entire reaction. We may need to consider a couple of these at the same time. So here are a couple of things that are getting more ordered, but they are still spontaneous or they're still favorable. So water freezing below 0 degrees or water condensing below 100 degrees, both phase changes, but we're going from a liquid to a solid or a gas to a liquid. And they're spontaneous, but they're getting more ordered. And the reason for this is that the delta S less than 0, that more ordered that we're getting, it's for the system. The second law refers to delta S of the universe. So if the delta S of the universe has to be increasing and delta S for the system is decreasing, something has to happen to the delta S of the surroundings in order for that to work out. And the thing that is happening is these reactions are exothermic. So these reactions give off heat, and that heat we already know where the heat goes. It gets absorbed by the surroundings. So the surroundings have an increase in temperature, which means their particles are moving faster because of kinetic molecular theory, and that is more disorder. So particles moving faster, it's messier than particles moving slower. So just change in entropy of the surroundings. If the reaction, if the system is exothermic, the surroundings absorb heat, you get an increase in the entropy of the surroundings. If it's an endothermic reaction or endothermic system, the reaction or system absorbs heat from the surroundings. So the surrounding particles go down in temperature, they move slower. This is a decrease in the entropy of the surroundings. So you can, for the surroundings, calculate the change in entropy. It depends on the temperature, and the temperature goes directly into this calculation. The change in entropy for the surroundings is the negative heat of the system divided by T. So negative heat of the system, if it's exothermic, that's going to have a negative heat in the system, which would make the negative of the heat of the system, we'd have a positive heat of system. So exothermic reaction giving you an increase in entropy. That's how that works mathematically. If we're at constant pressure, which we like to do, then instead of writing heat of the system, I can write delta H of the system because they mean the same thing. So the change in the entropy of the surroundings can also be calculated with negative delta H of the system divided by T. So entropy units are energy per Kelvin, usually reported as joules per Kelvin because they're smaller values. However, we are going to have to combine this with things like delta H. So don't forget to pay attention to joules versus kilojoules.